You wouldn't believe what horrible attributes we give to the word orthogonal eventually. Take my linear algebra course and you'll find out, much to your chagrin. So I think that was chapter 4 where we did orthogonal trajectories. Let me see. I don't know, I gotta look stuff up again. Oh, stop that. Wish you could experience my pain for a while. It'd be fun.
But then we'd have nothing to look forward to in our golden years.
Yeah, they call it golden for a reason. It's because how much you got to pay to try to stay functional. So 168 is what it looks like. 186, 168, same thing. Yes. Yeah, open your books to page 168. You might remember those 4 problems, just 4 problems. But there, you were supposed to, given 2 families of curves, prove that the families were orthogonal trajectories of each other. So, for example, suppose that this was one family of curves. Can you tell me what kind of a family of curves that is?
White middle class?
It's green. Does white middle class fit in there? Gosh, it doesn't even have a y-intercept. I think it's lower class. So it's a family of lines through the origin, different slopes, right? Yes. So if you were to draw these, you would have to draw a series of lines all going through the origin, all at different angles, right? Notice you don't get the vertical one though, do you? Not as long as m is defined. But you get everything else. M is called the parameter. And what you were supposed to do is show that that set of curves is orthogonal to this set of curves.
And what does orthogonal mean again?
I ain't telling you. So I will, but not yet. And that's a family of circles centered at the origin, right? Different radius values. Defined for all r's. 0, positive, negative, because I squared the r. So now we were supposed to show that those 2 families were orthogonal to each other. So now I get to answer this gentleman's question. I use the term very loosely. Gentleman, not question. So somebody want to remind me? What does perpendicular mean?
He's like, what?
Perpendicular, 2 lines at right angles to each other.
That makes sense. And their slopes are negative reciprocals?
Did you say something about naked reciprocals?
Negative.
I want to know. I want to party with this. Rim and River are going to be a good time. Perpendicular means 2 lines at right angles to each other. Pretend that those are at right angles. What does normal, I hesitate to ask, what does normal mean? Well, it's where you got a curvy line and a line that is perpendicular to that. In that case, where it's not just 2 perpendicular lines, but rather a curvy line and a straight line, we use the word normal. And what we mean by saying perpendicular to a curve is perpendicular to the tangent line drawn at the point of tangency. So if we were talking about, say, this point, we would have to find out what the tangent line is. And now the normal would be the line perpendicular to the tangent line, and therefore perpendicular to the curve. This is all stuff you really need if you have the misfortune of going on to Calc 3. And we'll talk about the normal vector and the tangent vector and, what you get, this vector, this one, and one that will be, that will form the complete three-dimensional coordinate system. Those are the axes that you have to use when you're flying in 3D space for something called yaw and roll and pitch. A plane can be off forward to back, it can be off side to side, or it can be off at an angle. And what you use are these three coordinate axes to align the nose, the belly, and the wing of the aircraft, especially something like a space shuttle where you don't have the pilot's instincts to fall back on. And you let the computer orient the curve in order, orient the ship in order to fly in curves and change directions and all of that. Anyway, here's what we're going to deal with today is the worst of the words called orthogonal. Orthogonal, the perpendicular was two lines. Normal is a line and a curve. Orthogonal is two curves. Say I want to claim that that curve is orthogonal to another. Well, what I'm talking about at whatever point of intersection we're interested in is I want their tangent lines to be perpendicular. So if I can draw another curve that is more or less with a perpendicular tangent line, now we would say that these two curves are orthogonal. And what you did back in Calc 1, back on page 168, was they gave you two families of curves and they asked you to verify that they were orthogonal to each other. You did that by finding their derivatives, their slopes, and showing that one slope calculation was a negative reciprocal of the other. Negative reciprocal, right? Slopes, perpendicular. Our problem now is slightly different. Notice that we are discussing this problem in the context of a chapter called differential equations, which somehow solves equations, with derivatives in them. So what they're going to do for us is not this, where they give us two families of curves, verify that they're orthogonal. They're going to give us one family of curves and say, find the orthogonal family. So let's do that in this nice simple case. Let's take one of these families of curves and show that the other family will be what we think it is here. So let's take the family of curves y equal mx and find its orthogonal trajectories. Well, what I want is a set of curves that has a negative reciprocal slope to that. All right, so in other words, what's dy dx here? So for the orthogonal family, or for orthogonality, there's a fancy word. You got to see what we make that word mean in linear algebra. That's really horrible. But for orthogonality, I would then need dy dx to be minus 1 over m. Now I got to solve the differential equation. So I got to put all the x's on one side and all the y's on the other. Somebody want to help me? Well, that wasn't hard. Pardon me?
M equals negative.
We will. The trouble here is that we're only doing this at the points of intersection. And what is m equal to? Okay. So what am I doing? replaced y with what it's equal to, and somehow went on to the next step all at the same time, which doesn't really happen in the real world. So that's y dy plus x dx equals 0. And now let's integrate.
One over 2y squared. X squared.
Why don't we call that r? Oh, let's call it r1. Where r, actually we can even leave that off. We'll just call it r, where r is equal to 2r1. Because we have degenerate cases here, right? R has to be positive, just like we do not allow m to be undefined here. Lines and circles centered at the origin, perpendicular at their points of intersection. And you will get to enjoy that.
So why does r equal to 2r?
Well, it doesn't. What's the derivative of a constant? So what's the integral of 0? Constant. We'll call that one r. So all of that was part of 9.3. There is one other little thing in 9.3 we have to discuss. You guys know how important mixture problems are in the real world, right? Well, in the real world, that's very true. I mean, if you go to a pharmacy and they have to actually make the medicines, right, for you, you want them to be able to do this well. The last thing you want is for some half-ass pharmacist to not know how to mix the proper dosage for your, I don't know, for your
Herpes
kind of
syphilis.
drug do you buy these days? I don't know. Whatever. So mixing, like you've done before, is kind of easy, right? You're going to take a 90% antiseptic solution and you're going to mix it with a 20% antiseptic solution, and you're going to get 5 gallons of a 40% antiseptic solution. Big bubbles, no trouble. We can do that. Any chemistry class, intro to chemistry, you'll learn that. But what if, well, things could get a little more sticky. Suppose that we've got a vat with 1,000, that holds 1,000 gallons in it. Or let's say liters. 1,000-liter capacity. And let's say that that tank is full of, what do you want it full of? Something with something, water with something dissolved in it. What do you want? Salt water? Sugar water? Alcohol water? Let's say that, let's stick with the traditional examples. Let's say initially the 1,000-liter tank is full of water with, let's say 1/2 kilogram of salt dissolved into every liter. All right, so I guess it's got 500 kilograms of salt in it. Salty water. Well, let's say that brine enters the vat. Let's say brine containing 1/4 kilogram per liter of salt enters the vat, the tank, at say, I don't know, how fast you want it to go? 10 liters a minute. So is it getting saltier or less salty? Less salty. Very
Less salty.
good. Geez, you're starting off with a half a kilogram per liter.
You're
and
gonna do a
putting
quarter.
Stuff in that's only a quarter kilogram per liter. What do you mean it's getting more salty? Gosh, you're adding a weaker concentration. Let's say that brine is drained away. From the well-mixed tank. Also at 10 liters per minute. Now that's necessary, but the rate that stuff is being added is the same as the rate that it's being drained away. Otherwise, we have to learn a different technique for solving differential equations besides just variable separability. That's all you need to know. Now you're going to be able to write an equation for me that tells the amount of salt in the tank at any time t. Anybody got it yet? That's a joke. You're not supposed to be able to do it yet. Let's let y equal the amount of salt in the tank at time t. The number of kilograms of salt in the tank at time t. How fast is the amount of salt changing? That's what dy dt is, isn't it? If y is the amount of salt at time t, dy dt is how fast that salt changes. Well, we're out of time, so let me just kind of do this fast. It's going to equal the difference between the rate that salt enters and the rate that salt exits. Well, how fast is salt entering? Well, it's entering at 1/4 kilogram per liter. But it's coming in at 10 liters per minute. So I guess that's going to be 10 over 4, 5 halves, 2.5 kilograms per minute of salt added in. How much is being drained away? Well, it's well mixed. I don't know what the concentration is, but I know that there's y kilograms and there's 1,000 liters because the amount that goes in is equal to the amount that goes out. So it's y over 1,000 kilograms per liter, also 10 liters per minute. So here's our differential equation, dy dt. Is equal to 5 halves minus y over 100. And now we have to solve that. So if I get a common denominator here, I guess I'll multiply top and bottom by 50, so 250 minus y over 100. So I've got dy dt equal 250 minus y all over 100. Or if we now separate the variables, we will get 1 over 250 minus y dy equals 1 over 100 dt. If we integrate both sides, we get minus the ln, the absolute value 250 minus y equals t over 100 dt, or t over 100 plus an arbitrary constant. Yeah, Ripper's getting tired. We can now find C because we know the initial amount. When t is 0, right, how much salt do we start off with initially? half a kilogram in every liter. So 500 kilograms of salt. So I get minus the ln, absolute value 250 minus 500 equals C, or in other words, C is minus ln 250. Now I can write the equation with a bit more specificity. I can say minus the ln of 250 minus y in absolute value is equal to t over 100 minus the ln of 250. Or maybe we'll get rid of the minus sign by erasing that, putting a plus there and putting a minus there. How am I going to solve for y?
To the power.
So e to the ln cancels, I get absolute value 250 minus y equals, well, I guess that's 250 e to the minus t over 100. What about the absolute value? Well, y starts out at 500, doesn't it? And it gets smaller and smaller and smaller, but it never gets below 250, so this in here is always negative. How do I get rid of the absolute value? Make it y minus 250. Now it's always positive. And you wanted a fully simplified equation, just put the 250 over there with that. Y equals 250 plus 250 e to the minus t over 100. How much salt is in that tank after 500 minutes? Plug in T equal 500. How long will it take for that tank to contain 400 kilograms of salt? Plug 400 in for Y, solve for T. I apologize for keeping you 5 minutes late. Now get the hell out.